All right. So suppose I have this electron coming in and goes into this experiment. And there are two possibilities. So here I put a detector. Here I put another detector. So now there are no complications about whether I make a measurement or not. I definitely make a measurement whether this one clicks or that one clicks. Okay, so I send out an electron. It passes through this equipment, and there's a 50% possibility that it will click here and there. In fact, perhaps it is better to take only this Z plus because we are not sure how this electron is constructed. It may just be some thermal random stuff, but here we certainly have, okay, if we look at this Z plus, suppose now I measure Lx, and it either goes up here, plus h bar over 2, or minus h bar over 2, and here are my two detectors. So either this one clicks or that one clicks. So I send one electron at a time. Okay, I send in one electron at a time. So I'm asked to make these things bigger, h bar over 2 and minus h bar over 2. Okay. So now I'm making this measurement, but you see the argument against this wave function collapse stuff is that we are following the Schrödinger equation through all of these processes, but then we are just throwing everything away and saying that, okay, the wave function just collapses either to this or to that. Okay? That is the Copenhagen interpretation. There is an alternative interpretation which is somewhat fashionable in social media, of course, among the scientists also, which you may hear every once in a while, so that, at least for your general knowledge, I should say a few words about it. And it's the many worlds interpretation. Okay, now this interpretation says, why stop the Schrödinger equation at that point? You are also an observer here. You are looking at this experiment. There are two possibilities, two possible paths that this object is going into. Okay, so these are my, let me move these measuring devices a little bit away from the experiment. Okay, so I have this psi z plus, which is a linear combination of psi x plus and psi x minus with a 1 over square root of 2, okay, constant. It says that this piece of the wave function is moving over here, psi x plus, and this one is going psi x minus. It says that, okay, so this is moving along. At this point, you also are a part of the quantum mechanical system. So what happens is, from this point on, a new universe is created. Okay? In this universe, this detector clicks. In the second universe that has been created, the other detector clicks. Okay? And the Schrödinger equation just continues integrating, okay, whatever is going on. So each time you have some quantum mechanical event like this, there's a new universe being created. Okay, so the number of universes that are being created are immense. Okay, so if I, for example, when I look at these lights, each photon that strikes a cell in my retina is a measurement. So all of us are creating incredible number of universes. Okay, lots of hands coming up, which is good. Okay, so in order to kill a dragon, you have created a bigger dragon, but it seems to be an interesting idea. Yes?
Is the collapse continuous or discontinuous in time?
The collapse in the Copenhagen interpretation is discontinuous. It is not reversible. Okay, what's important, another important point.
Only an interpretation, or do we know that from the equation as well?
No, you see, the Schrödinger equation is one thing, collapse is something else. Schrödinger equation is a linear, time irreversible. You can reverse the time, okay? And it's still deterministic in the sense that psi develops deterministically, okay? So if you are given an initial psi, you know what psi will do at a later time. It becomes non-deterministic only during the collapse. Okay, so Schrödinger equation itself does not contain anything about indeterminacy. Okay, so collapse is a different event, irreversible, nonlinear, so it's not really part of the same formalism as the differential equation. Yes?
You said that the detection is not irreversible. So what does that tell us about information globally?
Okay, watch YouTube videos. That's what I suggest to you. Okay, so this subject is an active area of discussion. Lots of things can be said about it, but we have not really studied information and what information does to it, etc. So things like decoherence, for example, increases the entropy, but okay, we are not really equipped to go into that detail at this point. Other questions? Okay, in any case, the Copenhagen interpretation made the original developers of quantum theory somewhat uneasy. They were uncomfortable with it, especially the older generation, people like Einstein, Heisenberg, and Schrödinger. Schrödinger was very upset with the Copenhagen interpretation, and in fact, Schrödinger said, "I'm sorry I had anything to do with quantum mechanics." And then after that point, he did not work on quantum mechanics, but other interesting stuff. In fact, Schrödinger's personal life makes very interesting reading, which we cannot go into in class, but I recommend you go to Wikipedia and such places and read it there. The younger generation, younger meaning people who were young in 1950s, people like Feynman and Schwinger and all that generation were quite comfortable with it. They said, okay, so that's all there is to know about nature, that's all we can know. It's nice that we can calculate what the collapse gives us, so let's just shut up and calculate. So that's the approach, but recently the ideas like these many world interpretation, etc., are attracting more attention. I think possibly because of the social media also, because these are interesting ideas that you have zillions of universes being born every microsecond. If you don't worry about things like conservation of energy and such things, of course. Okay. So let's get back to more reasonable. It's I think out of time to shut up and calculate. And also, since these interpretations are not really things that can be cast into an experiment and tested, okay, so even if there is a universe being born with every quantum measurement, we cannot make an experiment to test that, okay? So if it's not testable experimentally, it's not really science, and it becomes something like a belief. So you are free to believe whatever you like, and not much sense discussing it. Okay. So first of all, we'll need to, let me see if I want to say anything else. Yeah, okay. So since, okay, so if psi star psi is the probability density, okay, then it must be normalized. Okay, what does that mean? Okay, if I have this P of R and T, okay, dq bar, what is this? This is the probability that the particle is somewhere inside the volume, okay, which is defined by this integration. So if I just, let me make it simpler. Well, I shouldn't, I wrote it once. Okay, so this thing over all space should add up to 1. Okay? So let's do some examples, and we'll maybe I'll okay, we'll stay in one dimension for most of the time until we get to three-dimensional problems, where we obviously then have to put all the dimensions in. Okay, so as an example, suppose I have a psi of x, okay, is equal to, so I'm not putting time in here, so this is the psi at a certain point in time, is equal to some exponential form, e to the minus e x over x0 squared plus I, let's say k0 x. Okay, so this I k0 x is in the form of a phase, and I can always multiply this by some constant. Okay, so that's my wave function. And what I want is, I want integral from minus infinity to infinity, psi star of x, psi of x equal to 1. Okay, so let's just put this down in, minus infinity to infinity, a star a, which will give me a nice positive constant, e to the minus x squared 2x squared over x0, because I'm squaring it. What does the e to the I k0 turn into? What happens to that term?
Plus k naught squared x squared.
Careful. Okay, I have to multiply this function with its complex conjugate. Okay, so a is multiplied by a star. this piece here, of course, will be multiplied by 2, but the complex conjugate of this has a minus sign here. Okay? So the phase just disappears. So this is not going to depend on x. Yes.
2x squared over
x0 squared. Yes. Okay. Okay. A warning to you: nothing I put on the board is guaranteed to be correct, and usually it will not be correct. And it's your responsibility as a class to keep me honest, right? Okay. So what does this look like? This looks like when I square it. Okay, so just something like this. The
bell curve.
yes, it's a Gaussian. And then this width here is related to x0, for example. Over here, when x is equal to x0, it's e to the minus 1. If I look at the magnitude squared, it's e to the minus 2, okay, times the maximum. All right, so I have this integral which will come up a lot of times in our calculations. So let me make an integral table here. Minus infinity to infinity, e to the minus a x squared dx is equal to what? Okay, square root of pi over a, right? So this is going to be square root of pi over a, which is 2 over x0 squared. So it's going to be x0 times square root of pi over 2. But I want this thing to be equal to 1. So that means I can choose this a star a in such a way. I have a star a still here. I can choose this factor so that this is equal to 1. Okay, so I want this thing equal to 1, which means a star a is going to be equal to the reciprocal of that. So it's going to be 1 over x0 square root of 2 over pi. So a is in general a complex number, but I can, without losing any generality, I can say that assume that a is positive and real, in which case I get a is equal to 1 over square root of x0 2 over pi to power 1/4. Okay, so this process is called normalization. And if I put that a into that equation, this becomes a normalized wave function. Okay. Now, if I have a normalized wave function whose magnitude squared is associated with some probability density, well, I can use that probability density to find various average quantities. Right? For example, I can find what the average value of x is. So what would that mean? That means on the average, where is this particle, okay, if it has a wave function which looks like that. Okay, so let's write that. Okay, so the average value of x this is also called expectation value of x also, okay? Average value of x or expectation value of x. Actually, average value is a better, okay, expression. Expectation value sort of implies you expect to get that result, but that's not always the case. If you have a probability density which looks like this, its average is going to be somewhere over here, but you don't expect to get anything with that value because there's a low probability, right? Okay, so the average value of x is just this probability density times x times dx minus infinity to infinity. All right, so let's look at it for our case. The probability density is going to be A star A, okay, times e to the minus 2x squared over x0 squared. That's what we got over here. All we need to do is we multiply this with x and integrate. Okay, so what do we get?
0.
Okay, we get 0. Why?
Symmetry.
Okay, so because of symmetry, because this is a nice even function. Okay, so this exponential here is an even function, and this one is an odd function. So their product is an odd function. And when I integrate it symmetrically between minus infinity and plus infinity, I end up with 0. Okay, so that makes sense if this is the wave function or probability density function. You see, it doesn't depend on k0. You expect the particle, okay, to be on the average at the origin, right? It's nice and symmetric. Now, a useful quantity is the average of x squared. Yes.
Does x squared have any physical meaning?
Which x squared?
Right now we got
This one? Yes. Why? Okay, we have seen that the average value of x is equal to 0, but a very useful quantity in general in any statistics is what happens when I take values of x and subtract out the average value. Okay, so this is how far I am from the average value. On the average, this is going to be 0, right? Because that's sort of by definition. Okay, so x on the average will be average value of x. But if I square this, these are all positive numbers. So with this probability density, okay, I'm going to get the square of x giving me all positive numbers, okay, for values of x on this x-axis. Okay? Now, depending on the shape of the probability function, for example, if the probability function is something like this, then its average is again going to be somewhere over here. But the values of x cannot be very far from the average value of x. On the other hand, for this function, for example, the average value of x minus x can be bigger. But if I square this, okay, then the points on the right do not have a canceling effect for the points on the left. Okay, so it's a measure of fluctuation. It's a measure of how much x is fluctuating around the average value of x. Okay? So, in fact, this quantity, if you now average this, okay, now this is called the RMS value, okay, because I'll average this and then find the square root of this. So this is root, okay, mean, and I have this point here, square. Okay. Okay, so RMS value is how much a statistical object is varying around its mean value. Okay, so if you measure, I don't know, as a function of time, for example, the temperature in Ankara, okay, it may do something like this, hotter during the day, cold during the night, etc. So this is a measure of, okay, how much temperature is fluctuating. In another city, it may go something like that. There, the delta T is much lower, okay? So this is what we are going to call delta X or sigma X. So these are all same types of notation depending on whether you are a physicist or statistician or whatever. Okay, so let's see what we get out of this. So they are going to get minus infinity to infinity, a star a, e to the minus 2x squared or x0 squared, x squared dx. Okay, now things are not so simple. Why? Because this is even, that's also even. So the result is going to be finite. And in fact, the result has to be positive. Okay, because these are all positive quantities. Okay, that is positive, that's positive. The result of the integral has to be positive. Okay, so when you are doing these integrals in exam, homework, etc., always make sure that your result makes sense. Okay, so the average value of x squared, okay, is average of x squared. Okay, so average value of lots of numbers which are squared, which are all positive, so this has to be greater than 0. Also, just again checking algebra, anything that you evaluate a function of, something like exponential, for example, anything that goes into the argument of a function has to be unitless. Okay? You cannot have e to the 5 meters. It doesn't make sense. Okay? Why? Because exponential is defined in terms of a series. Okay? E to the x is 1 plus x squared over 2 factorial, etc. So if you have e to the 5 meters, 1 plus 5 meters plus 25 meters squared doesn't make sense. Okay, so anything that goes into a function has to be unitless. You have to check that. Okay, so now I have this e to the minus x squared is Gaussian times x squared. Okay, the way I like to evaluate these integrals is if I know this, okay, so if I call this result I, okay, it's a function of a. You see, if I differentiate this with respect to a, what happens? It brings down a minus x squared, right? So I don't want the minus, so I'll do it like this. Okay, so the integral minus infinity to infinity e to the minus a x squared dx is equal to actually minus infinity to infinity e to the minus a x squared dx. So that is exactly what I want. So it is equal to minus del a over this square root of pi over a. A is in the denominator. So when I differentiate it, I'm going to get a minus a half, right? So it's going to be plus a half with this minus sign times the same thing, but 1 less power of a, right? So it's the same thing, except that instead of 1 over square root of a, I'm going to get a 3 over 2, and there's a factor 1 half because of the square root. Okay, so let's go back here. So this is going to be equal to
1 over 4x0.
okay, you don't trust me and I will not trust you. Okay, 1 over 2a. Okay, so 1 over 2 times, okay, 1 over a, which is going to be x0 squared over 2, okay, times the rest of the integral,
Which is 1.
which is 1. Okay, great. So I'm going to get x0 squared over 4. Okay, so for our problem, what is the fluctuation in x? How much will my measurements fluctuate if I just measure x? On the average, I'm going to get 0. Okay? But how much is the fluctuation going to be according to this definition, or sigma x, which is equal to delta x, which is just square root of x minus average value of x squared. Well, in this particular case, I have this average value of x is equal to 0. Okay, so it's just going to be, there's an average sign here. So it's going to be square root of average of x squared. So it's going to be x0 over 2. Okay, so apparently, if I just evaluate all my measurements, sum them up, etc., and find the standard deviation, the statistical deviation, that's what I'm going to get. Okay, any questions? Yes.
If we take x0 to 0, do we get direct delta?
Yes, okay, so x0 going to 0 will be a function which will effectively be 0 at all places except the origin. Okay, so maybe I will write that down. Okay, so if I look at this equation, where am I? A 1 over square root of x0, 2 over pi e to the minus x, okay, 2x squared over x0 squared. I have to be careful because I'm writing the square here, so it's going to be 1 over x0 and the square root of this. Okay. If I look at the limit x0 going to 0 of this, okay, you can see that point x0 or point 0, x equal to 0, is a problematic point, right? I have a 1 over x0 here and 1 over x0 there. But otherwise, as x0 goes to 0, this is going to be such a big negative number for any finite x that this, okay, goes to 0, okay, for x not equal to 0. But also the area under it for any point which contains the origin. Okay, so if let me call it just f of x so that I don't have to write it. Is equal to 1 because it's normalized. Okay. So that is really the definition of the delta function, right? So this then just must be going to delta x.
So why there's a 2dx axis?
Well, just testing you. Okay. Any Other questions, comments?
I couldn't understand the last part. I mean, the minus epsilon to epsilon. Why we do this integral? I couldn't get that.
Okay, we have a function. When x0 is extremely small, we are going to get something which looks like this. Okay, so it goes, when x goes to 0, it's really has a very large magnitude. This is a function of x. So x0 is sort of the width of this. Okay, and the magnitude when x is equal to 0 is equal to 1 over x0. So it's extremely large, but the area under it is equal to 1. Okay, because we normalized it. Okay, because it was normalized. So in that limit, if you are interested in any point on the x-axis where x is not equal to 0, you get 0. But if you do an integral very close to this point from minus epsilon to plus epsilon, you get 1. Okay, and that's how delta functions behave. Okay, the area under the delta function is 1, but apart from the singularity at all other points, it's equal to 0. So this is one way of constructing a delta function. Okay, so, or you could also do something like this, right? You can take some function which is between, say, minus delta and plus delta, and with a magnitude of 1 over 2 delta, so that its area is equal to 1, and in the limit delta goes to 0, again, you end up with the delta function. So these are all different ways in which you can construct a delta function. Okay, other questions? Okay, I'll let you go. So most likely we'll meet Thursday at 10:30.